Hi, welcome to today's talk on the properties of electric charges. What are we learning? We'll do an overview of the properties of electric charges. We'll look at the types of charges, the direction of the force between charges, charge quantization, conservation of charge, conductors and insulators, conduction and induction. First, electric charge is positive or it is negative. Here is a very simple model of a helium atom. There are 2 protons, 2 neutrons, and 2 electrons orbiting. Again, this is a very simple, basic model of an atom. First, protons in the nucleus are positive. Electrons, we'll say orbiting, are negative. Protons and electrons have the same magnitude of charge. They just have opposite signs. Like charges repel. Here we have 2 positive charges. Notice that the force vector here is the force of charge number 2 on 1 is pointing away from charge number 2, and this is the force of charge number 1 on charge number 2, and they are repelling each other. The same would happen if these were 2 negative charges. Opposite charges attract. Here we have a positive charge and a negative charge. Notice that the force between these two is attractive. It is pulling the 2 charges towards each other. Charge is quantized. What do we mean by quantized? It means that some quantity occurs only in very discrete chunks that can't be divided anymore. In 1909, Robert Millikan discovered that if an object is charged, its charge is always a multiple of a fundamental unit of charge, E. That E is 1.60219 times 10 to the negative 9 coulombs. Coulomb is going to be our unit of electrical charge. Like we said, the charge is said to be quantized, meaning that the charge occurs only in discrete chunks that can't be divided anymore. So an object that is charged can have a charge of E, plus or minus E, say plus or minus 2E, plus or minus 3E, but never a fractional charge. Again, the charge on an electron and a proton is the same magnitude, just different signs. The electron is negative, the proton is positive. But take a look at the difference in the mass. The mass here of the electron is 9.11 times 10 to the negative 31 kilograms. It's pretty small. 3, 2, 1. The mass of the proton is 1.67 times 10 to the negative 27. On the order of about 1,000 times more massive than the electron. The neutron has 0 charge, but it has about the same mass as the proton. In a typical electrostatic experiment in which, say, a rubber rod or a glass rod is charged by friction, there is a net charge on the order of microcoulombs. Only a very small fraction of the total charge is transferred between any 2 objects, typically, say, between a charged glass rod or rubber rod or a PVC pipe like we used in our experiments. Charge travels easily from one type of material to another. Rubbing the 2 materials increases the area of contact, which makes it easier for this transfer process to occur. Charge isn't created when 2 neutral objects or rubbed together, the objects become charged because negative charge is transferred from one object to the other. One object gains a negative charge while the other loses an equal amount of negative charge, and so it's left with a net positive charge. When a glass rod is rubbed with silk, as it's shown here, electrons are transferred from the rod to the silk. So that means the glass rod carries a net positive charge and the silk a net negative charge. In insulators, such as glass, electric charges do not move easily through this material. We'll call it an insulator. A conductor, on the other hand, electric charges move very easily through it, say a copper wire. So how do things get charged? Well, one way to do that is by conduction. Let's say we have a negatively charged rod and a neutral sphere. The extra electrons on the rod repel the electrons in the sphere, which creates a local positive charge on the neutral sphere. On contact, some electrons on the rod are able to move onto the sphere, neutralizing the positive charges. When the rod is removed, the sphere is now left with a net negative charge. This is charging by conduction. Next, let's look at charging by induction. Let's do the same thing as we did with charging by conduction. We're bringing a negatively charged rod next to a neutral sphere. The sphere becomes positively charged just on this side here. It's still overall neutral. When an object is connected to a grounding wire or copper pipe buried in the earth, we say it is grounded. We can think of the earth as an infinite reservoir for electrons. It can accept or supply an unlimited number of electrons. We connect the grounding conducting wire to the sphere. Now, some of the electrons are able to leave the sphere and travel to the ground. Now we can remove the ground wire. The conducting sphere is left with an excess of induced positive charges. Then the remaining electrons will redistribute uniformly, and now there is a net positive charge. Next, let's look at charge polarization. Let's say we have a positively charged balloon, like we saw in the classroom. We got it to stick to, say, a wall because we now induced a charge locally here on the wall. Now we have a locally negative charged region of the wall. Opposite charges then attract one. All right, let's summarize. We know quite a bit now. First, charges are positive or negative. Like charges repel, opposite charges attract. Charge is quantized. This means that there are discrete amounts that cannot be divided. A charge is conserved. If one object gains a charge, the other one loses a charge. Conductors are things that charges flow very easily through. Insulators, charges do not flow very easily through. Conduction is charging by contact. Induction is charging by grounding. And finally, charge polarization. This is when one part of a neutral object temporarily acquires a charge. All right, thank you for listening. Rewind and review as necessary. Don't forget to complete and turn in your Cornell notes, and we'll see you next time.